Okay, merci. Okay, so let me just go back to where we were before. So yesterday I mainly talked about pointwise regularity and gave a few examples of functions for which we can either exactly compute or estimate their pointwise regularity. And then I focused on one notion of pointwise regularity, which is the Hölder exponent. So basically, I'll keep that for a few moments. We said that for a locally bounded function f, so we assume that f belongs to L infinity log. We say that f belongs to C alpha of x naught if there exists a polynomial p, which we will call the Taylor expansion of f at x naught, such that f of x minus p of x minus x naught is bounded by C x minus x naught to the alpha. And basically, the best possible alpha you can pick, which would depend, in general, would depend on the point x naught is the Hölder exponent. So the Hölder exponent h is the supremum of all alpha, such that f belongs to C alpha of x naught. Okay, so it's always positive because since f is locally bounded, you can always pick alpha equals 0. So this is a positive quantity, which can take any value between 0 and plus infinity, including plus infinity. Okay, an important notion, and we'll work a lot with that today and tomorrow, is the idea of multiscale quantities. So we want, this is a kind of continuous definition, but ultimately we want to have some algorithm which can numerically give some information about pointwise regularity. So we must make things discrete, and this is done through the use of multiscale quantities. And we pick a dyadic framework. Just we could pick a triadic or something else, but the dyadic is a tradition in harmonic analysis, so we we like dyadic things. Okay, so I'll use the following conventions. We'll use dyadic cubes. Well, most of the examples I will show will be in one dimension, so you can just think of dyadic intervals. And basically, what we like when we deal with regularity exponent or we see other exponent is this notion that you can deduce the pointwise exponent from pointwise log-log plot regressions of certain quantities defined on dyadic cubes. Okay, so if you pick a point x naught and we have this quantity d sub lambda, which is indexed by dyadic cubes, and if I call lambda j of x naught the dyadic cubes which contain x naught, if I can just by looking at these quantities through the scales, drawing a log-log plot, we expect to recover the pointwise exponent. Okay, so when we have this relationship between quantities indexed by dyadic cubes, so what we call multiscale quantities and pointwise exponent, we are happy. And you'll see a little bit afterwards what I mean exactly by being happy. Okay, so typical examples, for instance, I mentioned the local dimension for measures, and so maybe I won't recall what is the definition of local dimension, but you can just check that by taking the measure of what I call 3 lambda, which is the cube, which is no more a dyadic cube, but the cube centered at lambda, but 3 times wider. And you take this measure. So you need a little bit of overlapping. That's why we pick 3 lambda instead of just lambda. It would not work if we were just using lambda. Then you can, it's straightforward computation to see that you can use mu of 3 lambda as a multiscale quantity. And if you have if you start with a locally bounded function, and if you have exponents less than 1, you can take what we call the oscillation of the function on 3 lambda, which is the supremum minus the infimum. And it's also just straightforward to check that this is a good multiscale quantity. Good meaning that we have this, we can recover the other exponent just by log-log plot regressions. Okay, so the next point, and so I'm coming really to the core of the talk, is to use, we want to use wavelet coefficients instead of these particular quantities. And the reason is that there will be a very versatile tool which will be able to measure other notions of regularity and other type of exponents. So we at some point to shift from particular notions like oscillations to quantities constructed using wavelet coefficients. Okay, so what is the wavelet basis? Basically, everybody has heard of wavelet basis before. Did Jean-Lin teach you wavelet basis a long time ago? No, he didn't. He knew, he had the information, but yeah. Okay, so wavelet basis, basically you have one good function, or if you are in several variables, a collection of a few good functions, 2 to the d minus 1, actually. And by taking translations on dyadic dilations of the wavelet, if you made a good choice at the beginning, you can have an orthonormal basis of L2. And I just want to mention that I use the non-standard normalization for the wavelet coefficient, which is not the L2 normalization, but the good normalization for to make formulas a little bit simpler when we deal with pointwise or uniform regularity. And this is a picture of Ingrid Dobeschi's wearing one of our wavelets. So you see that wavelets are not useful just to do computation, but you can also wear them. And it was during, this is Dobeschi's wavelet number 64, because it was during the party for her 64th birthday, and she decided to celebrate her 64th birthday because we work in dyadic analysis. So 60 is not the right age to make a celebration, but 64 is much more fitting. Okay, so why use wavelet basis? I mean, there are many reasons, but for us, basically wavelets, and this is really an underlying theme in a lot of what I will talk about, are fitted to study data which present some self-similarity. Why? Because self-similarity, loosely speaking, I mean, there are some precise mathematical definition of self-similar processes, but loosely speaking, you have a kind of invariance with respect to shift. And since wavelets deduce from each other by dilations, wavelet coefficient on the wavelet coefficients, you will be able to unfold self-similarity properties of the data. And this is again a theme which is very recurrent in the wavelet analysis. You have the good news of fast decomposition and recomposition algorithm, which are actually faster than FFT. A very important idea, which I already mentioned last Friday, is that you have space representation, and this is a key idea in signal processing. Why could people discover a gravitational wave? Because it was not a wavelet basis, it was a Wilson basis, but the idea is the same, because gravitational waves have a sparse representation in the Wilson basis. And here it's also one of the reasons of the use of wavelet basis is that large collections of signals from very different origins also have sparse representation. And that means that it's not only useful to transmit information or to recover information, but also to do denoising, you need sparsity. And this is really what was used in the gravitational wave case. And also for very specifically for what we will be dealing with, the fact that you can characterize either a global, I mean uniform, or pointwise regularity by simple conditions on wavelet coefficient will play an important role. And this is really specific of wavelets. For instance, if you use Fourier basis, you can, I mean, you cannot characterize either, of course, pointwise regularity because of the Fourier system is not local, so it kind of mixes all the information everywhere. But even uniform regularity, you cannot characterize. For instance, on the modulus of the Fourier coefficients, the fact that a function belongs to C alpha. I mean, you have implication in both ways, and you lose something if you go both ways. Whereas using wavelet, you have characterizations, for instance, of the exact characterization of the C alpha spaces and almost characterization of C alpha of X naught condition. Okay, so these are a few reasons why we are happy to use wavelet. So for instance, a little computation, and maybe I will go fast on that because this is just a stupid change of variable, but just to show you that, for instance, so this is a slight variant of the Weierstrass function. You add the negative g's, so that it's easy to check that the series is actually convergent. And this is a slight modification of the Weierstrass function that was introduced by Mandelbrot because it satisfies, it's nice because it satisfies an exact scaling relationship, which is a relationship in purple here. And the good news, this is just this computation, is that because wavelet deduce from each other by translations and dilations, this scaling invariance of the Weierstrass function is reflected in an exact scaling invariance of the wavelet coefficients. Okay, so and okay, and if you have, for instance, if you don't have exact scaling invariance but stochastic invariance, and that's really the definition of self-similar processes. For instance, the fact that if you do if you perform a dilation on the variable, you get the same stochastic process up to some renormalization factor. Then you can also, this is exactly the same computation. So I go what did I write here? Yeah, it's an equality. I should have written the L also at the end. So you have equality in low up to a scaling invariance on the wavelet coefficient. So once again, if you have self-similarity on the data, either deterministic or probabilistic, you have this can be translated into properties of the on the wavelet coefficient. So in the case of a fractional volume motion, because you have also stationarity of increments, you can show that actually all the laws up to some renormalization, the laws of the wavelet coefficients are all the same. Okay, so as I said before, also an important information is the fact that you have characterization on the wavelet coefficients of uniform regularity. So I won't give details because this is well known. I mean, since a very long time. And but something that will be interesting for us if you want to do to apply wavelet techniques to do classification. This allows to define a parameter, which is a uniform regularity parameter, which is basically the best uniform regularity exponent of your data, which we call H mean. And you can compute this H mean by log plot regressions on the wavelet coefficient. You take a supremum of the wavelet coefficient, you do a log plot regression, And it gives you a nice parameter for classification. I will show applications. And also another important point is that if it's positive, it means that you can model your data by a continuous function. Even it has some uniform regularity. It's negative, it means that it's not possible. And this will be important for us later, because if you want to estimate Hölder exponent, as I mentioned before, you need to know that your function is locally bounded. And so the prerequisite basically is to compute this uniform Hölder regularity beforehand and make sure that it's positive. And if it's negative, we will see what can be done. Sorry? No. Okay, well, if it's 0, you cannot conclude, but I mean, usually, yeah, because you don't know. If it's 0, the function could be either can be just continuous, or but usually it's not just 0. I mean, you compute something positive or negative. Okay, so I'll use also notations for wavelets. I will index wavelets by dyadic cubes. Basically, it's essentially the support of the wavelet. I mean, if the wavelet was a Haar wavelet, it would be exactly the support of the wavelet. If it's a little bit more widespread, it's not exactly. But think of the index lambda as the support of the wavelets, and you won't make a big mistake. So we have wavelet coefficient, which I will also index using dyadic cubes. And also I will use a notation lambda sub j as a collection of wavelet coefficients at scale at level j. So it means that the wavelets are of width about 2 to the minus j. Okay, so I write the wavelet expansion of a function as the sum over j and the sum on dyadic cubes indexed by lambda j of c lambda psi lambda. Okay, so now the first point is the first challenge is to have a multiscale quantity based on wavelet coefficients that would do the job. And do the job is what I was talking about a little bit earlier. That means that you can recover the Hölder regularity just by pointwise log-log-plot regressions. And the idea is that, I mean, the important result is that there exists such a quantity. It's not the wavelet coefficient as at the very beginning of wavelet, people thought that wavelet coefficients could do the job, and then counterexamples were found, and another quantity showed up, and it's local suprema of wavelet coefficients. So I have this little picture where you see the dyadic intervals of different widths, and so for the interval, maybe I will just go here. For this dyadic interval here, the corresponding wavelet leader is obtained just by considering also its two neighbors, if we're in dimension 1. And then you take the supremum of the wavelet coefficients on all these, on a priori an infinite number of wavelet coefficients, all the wavelets which are localized inside this interval and of width smaller. Okay, so this is the wavelet leaders. And they do the job in terms of pointwise regularity. It means that you can recover, if you have some uniform Hölder regularity, you can recover by log-log-plot regressions the pointwise Hölder exponent. Okay, so just to illustrate, so this is, I go back to the typical singularities I mentioned yesterday. So for a curved singularity, I show you just log-log-plot regressions of the wavelet coefficients, which are localized at the just above the cusp. So here, since you have a kind of exact scaling, the wavelet coefficients which also have an exact scaling, and you have a nice straight line with a good slope if you use wavelet coefficients, and if you use the wavelet leaders, you have also the same thing. And the good news is that if you have a weird singularity like this chirp-like behavior, which has very fast oscillations and no more scaling invariance. Of course, the wavelet coefficients don't do anything. I mean, you cannot really draw a log-log plot here. But if you use the wavelet leaders, you restore, in some sense, the good slope, and you get something which is almost 0.6. I mean, almost the right exponent. So it's kind of strange because here you don't have self-similarity here, and using wavelet leaders is a kind of way to nonetheless to create a kind of self-similarity on the data when it does not exist. Okay, so that's what I was just saying. So I was saying that you can do you can try to measure Hölder exponent if your data are locally bounded, and the exponent h mean will tell you that, and it has to be positive if you want to do it. So these are a few examples of data for which we are interested in studying. For instance, internet traffic. I talked about this data yesterday at the very beginning, or heartbeat intervals also, for which you see that if you make log-log plot regressions, you have something negative. So it means that really it does not make sense to try to analyze even the definition of the Hölder exponent does not make sense for such data. Okay, so in that case, we would like to have other notions of pointwise regularity, which would be okay for such data, and that would mean that if the h mean is negative, that means that in some sense you have negative exponent. So what does that mean to have a negative exponent? Of course, you could say, okay, I have a nice behavior like 1 over x, which would be a negative exponent. But since you want your singularities to be everywhere, such a definition would not work. So it could be used for isolated singularities, but if you have, for instance, a dense set of singularities, it would not make sense. So is there a definition of pointwise regularity which allows for negative exponents? And actually, the answer was given a long time ago by Calderón and Zygmund, and they introduced a very beautiful notion which they called the TP-alpha regularity. And the idea, okay, I think the simplest way to see it is to rewrite pointwise this definition by saying that if I know what is the right Taylor polynomial, and I subtract it, and then I take a supremum on a little ball of radius epsilon, then this supremum must scale like r to the alpha. So this is the way really to present pointwise Hölder regularity as a local L infinity norm, actually, that you are measuring. So this is okay if your function is in L infinity. If it's not in L infinity, but maybe just in LP, you can replace the L infinity norm by a local LP norm. And this is really what Calderón and Zygmund made. And their motivation was completely different from the one I mentioned. They wanted to, at that time, there were the results on regularity of solution of PDEs were, in the elliptic case, were clear and well known as regards uniform regularity. For instance, if you have a Laplacian U equal f and f is in C alpha, then U is in C alpha plus 2. So you gain 2 in regularity. And they were interested in knowing if you have also a pointwise version. If you have Laplacian U equal f with f C alpha at x naught, what can we say about U? And they realized that using pointwise Hölder regularity is not good. And the idea is really, you can understand it really on this line. It's not good because it's a local L infinity norm, and they knew that L infinity is not a good space. Okay, but LP is a good space. Good from their point of view, and using local LP regularity and expressing regularity in terms of these TP alpha spaces was much easier to prove regularity theorems for PDs, and that was really the motivation. But of course, we can use that definition in this other context and say, okay, maybe this is a good notion of pointwise regularity for function in LP. Okay, so you define the p-exponent just like the other exponent, just as you take the best possible exponent alpha in the definition of TP alpha. So the case p equals plus infinity is exactly the Hölder's case. And okay, you have this funny normalization, which is good, so that nice singularities like cusp have exactly the same. This is just a kind of good normalization, so that in the nice cases, the exponent, the p-exponent and the Hölder exponent is the same. And the good news is that, okay, now it gives indeed a good notion of regularity of negative exponents. The p-exponent can take values down to minus d over p. D is a dimension of space. Okay, so this is interesting. So this is one of the interesting points. And so I was mentioning that this uniform Hölder regularity, the exponent h means, allows to tell you if data belong to LP, and you have another tool to know if data belong. If you can model data by a function in LP or not, and this is done through the Wavelet scaling function. So basically, the definition, so there is a complicated definition using limit of log, but you must think of it by the top definition, which is not a clean mathematical definition, but basically you compute little LP averages of the Wavelet coefficient at each scales, and you make a log-log plot regression, and that gives you the Wavelet scaling function. So if it's positive, then the data belong to LP, and if it's negative, then the data don't belong to LP. And this interpretation, just I don't want to go too much into that. It's not very interesting. Just by embeddings between LP spaces and Bézard spaces. I mean, this definition at the top is fitted to a Bézard space, and you want information about LP regularity. Okay, so for instance, I'm using LP here. So for the real amateurs of harmonic analysis, one also important point is that you can go down to p less than 1, and then you have to replace LP by HP. There are these space HP. So if you have not heard of HP, you can forget this remark. And just the good news is that the wavelet characterization of LP and HP are the same. So if we are in the wavelet world, we don't see the difference. But for instance, if you have a probability measure, which is far from being, I mean, usually a continuous function, I mean, usually it doesn't even have a density, then if it has some sparsity, so I mentioned the box dimension yesterday, if the box dimension of its support is strictly less than D, then there is always a P for which you can, your data belong to actually to HP. And you can do this analysis. So basically, these wavelet tools that I will introduce allow to deal without any additional assumption to deal with at least with sparse, I mean, sparse probability measures. By sparse, I mean the support is less than this. So, for instance, the measure on the counter set that I mentioned yesterday, so exactly satisfies that. We computed its box dimension, the box dimension of the triadic Cantor set, and it was strictly less than 1. So this theorem means that there is a P, I don't remember which P will work, for which you can actually, the Cantor measure belongs to the corresponding HP space. Okay, so this is a wavelet scaling function. So it has an interpretation in terms of turbulence spaces. So I also don't want to go too much into that. And the good advantages of the wavelet scaling function. So for basically, you want to compute the wavelet scaling function for two reasons. One, just because it can also supply nice classification parameters for data. So you can just say, hey, I'm computing this, and this will allow to, for instance, to tell me if data fits a certain model or not. This was actually the very first introduction of this scaling function was done by Kolmogorov in the 1940s. And of course, he was not using wavelets, which did not exist at that time, but he was using an alternative definition without wavelets. And he did exactly that. I mean, he was working on turbulence at that time, and people were wondering if you could model turbulence data at small scale by fractional Bourdon motions. And the answer was no, and it was not a theoretical argument. It was just computing this scaling function, which is a straight line for fractional Bourdon motion, and is a nice banded curve for turbulence data. Okay, so this is one use, and actually it was the first motivation in the introduction by this scaling function, which we should really call it the Kolmogorov scaling function, rather than the wavelet scaling function. But for a long time, sometimes people were not sure that the two were coincide. So the two names remain. Anyway, so it has nice, I would say, functional analysis properties. And okay, this is just to show you on some. So I showed in 2D on images because it's nicer. We made the computation of wavelet scaling functions for characteristic functions, either for a characteristic function of a disk, a smooth domain, and you expect the wavelet scaling function to be constant and equal to 1. And for instance, for p equal 1, if you do the log plot regression, you get 1.03, so something very close to 1. So this is just to show you that you can do numerics, and you get, I mean, it's a sharp tool. And for the Van Core snowflake, so the characteristic function of the part in white, the wavelet scaling function must also be constant and equal to about 0.74. And for p equal 1, you get 0.75. So it's also, and you would see the log plot regressions on the left, and on the right, the scaling function. Okay, so this is just to show you on mathematical objects. And now if on pictures, so I'm just showing you pictures because it's nice. So Romanesco cauliflowers are a typical example of fractal sets. So you also wonder if the picture is fractal. And so in that case, you see that the H mean, so in the middle, you see the log plot regressions for the computation of H mean. And okay, you see the H mean is positive, so it can be modeled by a function in a C alpha space for a positive C alpha. And as expected, since the data can be modeled by L infinity function, the wavelet scaling function is positive for all values of P, which we see. And the Fern is intermediate. The H mean is slightly negative. So if P is too large, the data won't belong to LP. And you see that because the wavelet scaling function goes below 0 for P large enough, for P larger than 2.26, actually. And the satellite photograph at the bottom is one of the worst we computed with a very negative H mean. And you see that essentially for all values of P, eta of P is negative. So it's not very clear for the small values, but it's much more negative than the previous one. So this shows you that you can do also classification using this function. I mean, for different pictures of different scaling functions. Okay, so this is a little summary of the results. Okay, so I wanted to mention sometimes people are kind of shocked when I said you cannot model data by, for instance, locally bounded functions, because images are given by values between 0 and 1. I mean, by gray level. So you say it's a function that takes values between 0 and 1. It's it's bounded. So why don't I get an H mean which is negative? Where do I get an H mean which is negative, though the data are bounded? And the answer is that, and this is really the spirit of wavelets and multi-scale analysis. You don't look at the actual value of the data. You make log-log plot regression, so you see how the values, actually how averages evolve during scales. And even if at the end the data takes values between 0 and 1, basically the dynamic at several scales could indicate that your data are not bounded. I'm not sure if I'm making myself clear. For instance, I mean, in the case of an image, actually, the right modeling for an image would be much more like a measure, because it's if you have a picture, what you do is I mean, the values of the image at 1 pixel is just the number of photons that have been captured in the pixel. So it's more like local averages of a measure, which is just the light which is absorbed by the photograph, and an image is just a discretization of this measure by taking local averages at a given scale. So as soon as you think about that, if you have a dynamical view and you look at averages at different scales, you will realize that actually you are looking at a measure. Whereas if you just look at the last scale, you say, hey, I have data between 0 and 1, and that's a function. But that's the wrong point of view. You want a kind of multi-scale approach. And if you have that, it's no more a paradox that functions which take values between 0 and 1 cannot be modeled by locally bounded functions. This is an important point. And
the averages are still bounded, but they are not growing. I mean, it's more like you're taking the derivative when we.
Yes, yeah, exactly. Yes, you are. Okay, basically you have a measure, you're taking little averages of your measure on squares, and that's really what a camera is making. And then for a picture, you reduce that to have something between 0 and 1. But okay, if you took an average at a smaller scale, you would not have the same reduction, and so
it's relative to the scale.
Yeah, it's relative to the scale, exactly. And you can reveal that by doing a multi-scale analysis, like a wavelet analysis is exactly doing. And basically what it does is, okay, I have these final averages at the smallest possible scales, but I have also all the rougher averages. And if I look through all the averages, then I will see that in some sense the dynamic of the multi-resolution shows up and give me self-similarity exponents, for instance, which are not compatible with a bounded function, because at the end we are not looking at a bounded function. Okay, this is subtle, but it's very important. Okay, so this is, okay, I'll show today and maybe a little bit more tomorrow also some marathon runners data. And this is the Wavelet, for instance, the Wavelet scaling function from for their heartbeat intervals. So you as a function of time, you look at the time between two consecutive heartbeats, and you do a Wavelet analysis of these signals. Okay, so p-exponents. Let me come back to p-exponents. So it take, as I mentioned, it can take negative values, and this is really what we wanted at the beginning. And okay, the first step towards going beyond just a pointwise regularity analysis for one exponent is to consider the whole collection of p-exponent as a function also of p. Okay, so for some functions, the p-exponents at a point can differ. So they can be the same. For instance, for this nice cusp-like behavior that I showed, they are all the same, and they are the cusp exponent. So for let me write it down. So for the cusp is x minus x naught to the alpha. So at x naught, you have for all p, h at the point x naught is equal to alpha. Okay, so you taking different p exponent, you don't see a difference. But for some other more sophisticated singularities, and this is where we are really starting to do some classification of singularities, the p-exponent can differ. So they as a function of p, it cannot be any function of p. Of course, basically it's a consequence of kind of pointwise Sobolev embeddings. You have a few properties. Is there something in the chat? Random step function have in relation to system of ADP. So Brownian motion. Okay, Brownian motion is too simple for us. It has the p-exponent. All p-exponent will be the same. Relation to PDE. I would say no, because okay, this is really what I was mentioning with Kolmogorov's finding the fact that you cannot model, for instance, turbulence by using Brownian motion or fractional Brownian motion, and the reason is really the fact that the singularities of Brownian motion or fractional Brownian motion are everywhere the same. I mean, the Holder exponent is everywhere the same, and the p-exponent coincides with the Holder exponent everywhere. And as a consequence, the Wavelet scaling function I was mentioning is a linear function, which is not the case for turbulence, and which is considered, it's not a mathematical proof. I mean, mathematically, as you know, we don't know anything about the singularities of the solution of Navier-Stokes equation. And turbulence is even worse than Navier-Stokes equation because it's, in some sense, the limit when the viscosity goes down to 0 of Navier-Stokes equation. So it's even worse. And but physicists really interpret the nonlinearity of the scaling function, and I will come back to that maybe in a few minutes or later, as a signature of the fact that there are different singularities at different points. And I made some allusions to that last Friday, if you remember, when I showed the Riemann's function, and we'll come back to Riemann's function in a few minutes, which also shows up in some explicit computations and can be done in the framework of turbulence, which are, and Riemann's function has really a whole collection of different pointwise singularities. Okay, so the short answer is no. Okay, so okay, so the other good news is I was mentioning the fact that for older regularity, you have these wavelet leaders, which are the good multi-resolution quantities to perform to recover the older exponent, and there are p leaders which can be computed and just play the same role for the older for the p exponent. So I showed exactly the same picture, but you see the p leaders differ a little bit from leaders. For leaders, basically the idea is that you are estimating local L infinity norm of the function, and we have the local supremum of Wavelet coefficient, and here we are estimating local LP norm of the function, and we have local little LP with some normalization, but basically local little LP norm of the Wavelet coefficient that plays the role of the leaders, and making log-log plot regression, you get the p exponent. Okay, so this is just said, and so this is a joint theorem with Clotilde Mello, that indeed you can recover locally the p exponent from pointwise log-log plot regressions of p leaders. So just to show you numerically, in the case, so two singularities, either a Cuff singularity or a chirp singularity with negative exponents, and the leaders. So using leaders is forbidden because your data is not locally bounded, and indeed, if you do log-log plot regression of leaders, it's misleading. I mean, it looks like you have a slope, but it's just a kind of saturation of the leaders, and it doesn't give the good exponent. But if you do p leaders, you can estimate in both cases more or less well as the negative regularity. So this is just to illustrate the theorem. Okay, so we can use the p exponent as a point, as a kind of first classification of singularities, and I will show a few examples. We can go further, and I will give you basically the whole picture here, what we call the fractional exponent, which is a function of two variables. So one motivation is that there are some data which are used in modeling for which no p exponent will work. So for instance, the most classical one is Gaussian white noise. I mean, it's sample path. It's not really sample path. They are distribution. I mean, they are Schwarz distributions. They are not functions. They don't belong to any HP or LP space, and you would like to still to have some information, and it's pointwise regularity. And so we define the function for this type of data, or for any type of data, we can define a function which basically gives the whole picture of the pointwise behavior. And the idea is that, okay, we can, if we have for instance, here a Schwarz distribution, not a function, we can take a fractional integral. So if you take a fractional integral of large enough order, your function your data will belong to LP, and even will be locally bounded. And then you can compute p exponents of your data. Okay, so now we have at each point we have a function of two exponents, the p exponent, and actually it's better to write the properties to use 1 over p instead of p. So I will use q equal 1 over p, and the order of fractional integration. And the idea is that when it's well defined, it gives you I mean for the indices S and Q for which it's well defined, it gives you the whole information on the nature of the singularity. So I will, this is just a kind of anti-statement. So I will show in a few examples what I mean exactly by that. So the first remark is that we really don't know much about this function. We can work out a few examples to see what it can look like. We know what it can look like for when x0 is fixed. So at a given point x0, we know, for instance, which functions are fractional exponents. So there have been several partial results, and I don't want to go too much into that. And these are exactly the conditions satisfied. It's not very interesting. It just tells you that it's not any function, just like p-exponent were not any function. Similarly, fractional exponents are not any function. But what we really do not know is what this function can be as a function of x0. So if you consider the hf of x0 is at the bottom, S and Q. For a fixed x0, we know what it can look like, and we have some idea of what it means for the singularity at x0. But now if we look here at the function of x0, so as really a three variable function, which function can this be is really not clear. Even for p-exponent, it's a completely open problem. For instance, for Hölder exponent, we know which functions are Hölder exponent as a function of x0. It's I mean the technical answer is that they are the limit of continuous functions. So it's a nice characterization, and you can construct nice examples. For p-exponent, the problem is completely open. So for instance, knowing, so if you're interested, it's a very nice problem. I fix a p, even for p fixed, but different from infinity. The function h done h, the p-exponent at x. What do this function look like? We really don't know. And we know we just have a negative information. We know that it cannot be just les min of continuous function. It must be much more subtle, because for instance, if p-exponent can take negative values, and continuous function which takes negative values cannot be a p-exponent, because we know that on a dense set of points, the p-exponent has to be positive. So if it takes negative values, it means that it has to be extremely erratic and everywhere discontinuous. So understanding just this is really a sub problem of the general problem, but knowing for a fixed p what this function look like, it's just a big open problem, and we have no idea of what that can be. And this is really important, because when we perform multifactorial analysis, I will come to this tomorrow. We get some information about this function, and we don't know at all we don't really know what it means. It's because we just don't know what these functions can look like. Okay. So I would like to show you a few. I'll go directly. Okay, to show you what this function h of s of q really means on the data, and this will be a kind of introduction of tomorrow's talk about chirp and oscillating behavior and this kind of thing. So I mentioned cusp, the simplest singularities, and the normalization I gave. So taking, let me go back to the definition. When I take the exponent minus s, this is also just so that it's constant for cusp. So for cusp, simplest possible singularities, this function is constant. Okay, actually, you can introduce basically the simple singularities. You can define them by this an apparently much simpler, much less restrictive conditions. The fact that the partial derivative of this function at a given point is 0. This implies that h of S and Q is constant, and we will call that canonical singularities, and that really means singularities that will have the same behavior, which will look like cusps. Okay, so this is the first point in the classification of singularities. And when this derivative is negative, we will say that we have an oscillating singularity, and we define the oscillation exponent as this derivative. So for instance, and I didn't show this type of singularities last Friday. This is what we call lacunary singularities. And the idea, maybe it's not very clear here, is that you have a kind of cusp-like behavior, but you raise it, the older exponent is h because of very thin, like thin teeth of cones, so that you see if you average it, and this is what you do when you do when you compute p-exponent, you take local LP norms. These very thin cones will almost disappear, and the p-exponent will differ from the older exponent. Okay, so this is types of singularities for which p-exponents actually are not constant and differ from the older exponent. Okay, so this is an example of what I was mentioning at the beginning, the fact that all p-exponents may differ if the data are not cusps or cusp-like. And okay, this may seem a little bit strange and maybe very exceptional, but they are important, and they are important because in important classes, for instance, of stochastic processes, it has been proved that such singularities show up. So they don't just show up like in this very nice way, but they show up in the sense that you can express the fact that the p-exponent changes with p. If you look at it as a function of 1 over p, by the fact that a certain derivative vanishes or does not vanish, and if it changes with p, it means that this derivative does not vanish, and you call that the lacunarity exponent. And for some Levy processes, which are a very important class of stochastic processes in probability, there are singularities where this lacunarity exponent does not vanish, so which look a little bit like that, except that if you look at the sample path, you don't see this precise picture. Okay, so it's important because it shows up in some natural phenomena. And the last, and I will stop by that. The last example is the typical example is the chirps. And for chirps, okay, you have, for instance, for this function, the exponent is h plus beta s. And okay, so this is what we will call balanced singularities, and it's different. For instance, if you have a chirp and you look at the p-exponent, the p-exponent does not change. Okay, so if you just look at p-exponents, you don't see the difference between this chirp and the cusp. Okay, so it's different nature from the previous one. But you see that it's different from a cusp because when you take a primitive, for instance, because of the oscillation, I think I mentioned that last Friday, because of the oscillation of the sign, the older exponent will increase by more than 1 if you take a primitive. Okay, this is just a nice integration by part exercise. And so and this explains why we have to play with both exponents. I mean both levier, both tools, looking at p-exponent and also taking fractional integrals if you want really to draw differences between this kind of singularities. And in that case, you can see that a good definition for such singularities is to consider this derivative is 0. That what I was saying is the p-exponent does not change, and you can define some exponent which is really attached to this behavior by so this is a little complicated here. I mean, I won't explain why this is the right quantity. It's a difference of two partial derivatives of the but the important picture is to keep, I mean, is to see that you can attach exponents which allow to draw differences between these three typical behaviors: cusp, this lacunarity comes where you have lacunary singularities, and chirps like that, behaving like sine 1 over x. And the reasons for comes, as I said, is that they really show up in some stochastic processes. For this type of singularities, I don't know any class of stochastic processes where such singularities shows up, but there is no theorem either saying that they don't show up. But one motivation, as I mentioned last Friday, is that they do show up in quantities related with, I won't say in turbulence or such things, because as I said, mathematically, we don't know anything, but quantities related with turbulence. And there are actually having numerical methods which would allow you to say, okay, I measure the velocity of turbulence, and indeed there are this type of behaviors would be very important, for instance, because there are many models of turbulence at small scales which are in competition, which have been proposed by physicists, and some predict behaviors like that and some don't. So having a numerically robust method that would be able to say there are such singularities or there are not such singularities in the data would be an important progress in the comprehension of turbulence, which is for physicists is really one of the big open question. Okay, so I'm already past one hour, so I will stop here. And tomorrow I will give some ideas about how to put in evidence on data the fact that you have or you don't have this kind of singularities in the data.
Thank you very much.
Thank you.